Very good afternoon, students. So myself Dr. Jhumpa Mukherjee from Department of Chemistry, Damdam Motijheel College, and today we will be learning about a concept of chemical bonding which is called molecular orbital theory. The basic difference between valence bond theory, which you have already learned, and molecular orbital theory is that in valence bond theory we have considered that while forming chemical bonding the electrons are localized on top of the atom, and in molecular orbital theory we will be learning that the electrons are basically delocalized on top of the whole molecule. Let me tell you about the topics which I will be covering today. Introduction to molecular orbital theory, then comes the linear combination of atomic orbitals or LCAO concept, where you will be learning about bonding molecular orbital and antibonding molecular orbital. Then we will be learning about difference between atomic orbitals and molecular orbitals, which is very important. Then after that, relative energies of molecular orbitals, energy level diagram. Then there are certain rules to fill up these molecular orbitals, and order of energies of various molecular orbitals, and also we will be learning how to calculate the bond order and some analysis which will be dependent on this bond order calculations. So first let us discuss about why we needed this molecular orbital theory. So valence bond theory actually fails to answer certain questions like why helium He2 molecule does not exist, or why oxygen is paramagnetic. In 1932, F. Hood and R. S. Mulliken actually came up with a new theory which is known as molecular orbital theory to explain all these questions mentioned above. Molecular orbital theory is actually, is much more accurate than valence bond theory. And there actually we considered that the electrons are delocalized on top of the whole molecule, but in valence bond theory we have considered or imagined that electronic orbitals does not cover the whole molecule, it is localized on top of the atoms. So if you look at this picture, you will understand that how we can differentiate between valence bond theory and the molecular orbital theory. You see here the electrons are localized on top of the atoms, but here in molecular orbital theory you can see the whole electron cloud is actually delocalized on top of the whole molecule. So first let us consider about the in phase and out of phase wave combinations. So as we start to form the molecular orbital, basically we take two atomic orbitals and we form only one MO. But according to the rule of quantum mechanics, you know that orbital cannot be simply appear or disappear at our wish. So there should be same number of possible allowed sets to electron quantum numbers. So what is the meaning of that? Like if we combine two atoms to form two atomic orbitals to form MO, then we will be ended up in forming two molecular orbitals, not only one. So that is the basic concept. So we will have two molecular orbitals because in the beginning we had two atomic orbitals, so we will have two molecular orbitals. So for that we have to consider two kind of combinations. One is in phase combination and another is out of phase combination, that we know also. While using quantum mechanics, we know that there are two kind of combinations occur while doing this kind of overlapping. So here you see two hydrogen atoms are there. They can combine in out of phase combination and in phase combination. Here you see in this one, this is actually out of phase combinations, and this one is basically in phase combinations. Waves with same phase will interfere constructively and that will increase in amplitude. So this is basically a constructive interference, and you will see here that the increase in the amplitude takes place, and while when opposite phases combine, there will be destruction of the amplitude which occurs here. So when this kind of destruction occurs, a antibonding molecular orbital is formed, and while the constructive interference is happening, that time we are getting a bonding molecular orbital. In these pictures also you can see the same thing. When constructive interference takes place, waves combine so that the resulting wave is bigger than the original wave. So this blue one is the sky blue one is the first wave, and the red one is the second wave, and when they combine constructively, then we will get the third wave, which is called the resulting wave, and the amplitude of this wave is much bigger than the waves which we took for constructing this wave. And in the destructive interference, what is happening, you see, this one is the this sky one is the first wave, and this red one is the second wave, and when they combine destructively, then what happens, you see the resulting wave, which is actually has decreased in amplitude. So these are the two things we have to remember while forming the constructive interference and destructive interference. Now let us learn about linear combination of atomic orbitals, or LCAO. So as you know, electrons may be considered either of a particle or wave in nature. An electron in an atom may be described as occupying an atomic orbital or by a wave function psi, which are basically the solution of Schrodinger wave equation. So electrons in a molecules are said to occupy the molecular orbitals. The wave function of a molecular orbital may be obtained by linear combination of atomic orbitals. So first we have the wave function for the atoms, and then when we combine these wave functions for the atoms, we will get the molecular orbital wave functions. So and that is happen due to the linear combination of atomic orbitals. So let us consider like two atoms A and B, which have atomic orbitals described by the wave functions psi A and psi B. So the wave function for atom A is psi A, and the wave function for the atom B is psi B. So electrons of these two atoms overlap, then the wave function for the molecule can be obtained by a linear combination of the atomic orbitals, what, psi A and psi B. So this happens due to the subtraction or addition of wave functions of atomic orbitals. So we can write, you see, psi MO is equal to psi A, psi MO is equal to psi A plus minus psi B. So one is constructive interference and another is destructive interference. That means once we can write psi MO is equal to psi A plus psi B, and then we can also write psi MO is equal to psi A minus psi B. So this is basically constructive and this is destructive interference. So here you can see in this picture, you can see both kind of overlap has taken place, and this one is a constructive interference, and this is a when the atomic orbitals are combining out of phase, then we are getting a destructive interference, and this is called the antibonding molecular orbital. And when there is a in phase combination, we are telling that molecular orbital as a bonding molecular orbitals, and we represent them like this. You see atomic orbital 1s, and this is also another atomic orbital 1s, and then we get in phase combination, which gives us this bonding molecular orbital, and the out of phase combination, which gives us the antibonding molecular orbital, and this is much higher in energy compared to the bonding molecular orbital. So now I think the concept of bonding molecular orbital and antibonding orbital molecular orbital is clear to you now, but let me tell you another time that what is bonding and what is antibonding molecular orbital. So when there is an in-phase combination, that is a psi MO formed due to the positive interference of psi A and psi B, then the bonding molecular orbital is formed. This is a constructive interference, which I have told you earlier, and the probability density increases due to formation of this bonding orbital. Okay, and then for antibonding orbital, the opposite thing. When the combination is out of phase, that is psi A minus psi B, then the antibonding orbital is formed, and this is a destructive interference occurring. So I think now you have understand that how bonding and antibonding molecular orbital is formed. Now let me give you an example of the formation of bonding and antibonding orbital in a molecule, which is the simplest molecule, which is H2 plus. So here what happens, actually one atom is hydrogen and another one is H plus. So what happens here, you have how many electrons? One is 1, that is one electron is there, and inside the nucleus there is one proton. But in H plus you have no electron, but there is a proton in the nucleus. So you see here we have shown that this plus sign, this denotes the proton, and this is the electron present in the molecule. So what happens between these two nucleus which are positively charged, there will be a repulsion, right? And here in between the nucleus and the electron, in between the nucleus and electron, there is a attraction force happening, and this way there is the formation of the bonding and antibonding region. You see this part, this blue part, sky blue part is antibonding region, and this red part, red shaded part, this part is basically is describing the bonding region. This way the bond is formed. Here you can see there are two protons plus one electron, as I have told you that in both of these hydrogen protons are there, but in one hydrogen only you have electrons. So two protons plus one electron. This is giving rise to this dihydrogen ion. Now let me show you how the bonding and antibonding molecular orbitals are formed while combining two s orbital to form a sigma bond. So you see here that when two 1s orbital, actually these are the representation of the wave functions, they combine constructively. So this kind of molecular orbital will be forming. This is called bonding orbital. Bond is a region of constructive interference. So this part is actually formed due to the constructive interference. And then another orbital which we need to form is the antibonding orbital. Here you see two opposite phases, they combine, and here is the antibonding orbital. So you see here there is a nodal plane, and in this nodal surface actually we considered that the electron density is 0 here. So basically this is a destructive interference, very low electron probability is there, and this basically does not contribute to the formation of the bond. If we see the formation of the molecular orbital diagram of H2, you see there is a two 1s orbitals are there, and due to constructive interference there is a formation of sigma bond, which is the bonding MO, and then due to destructive interference, there is a formation of the antibonding orbital, which we denote as sigma star. So we denote the bonding orbital as sigma and antibonding molecular orbital as sigma star. And this is atomic orbital of one hydrogen, and this is atomic orbital of the other hydrogen, and energy generally increases in this way. So you can see the bonding molecular orbital is having the least energy, while the antibonding orbital will have the higher energy. So why this happens? Because you know that the potential energy decreases as the electrons move into a region that enables it to see that maximum amount of positive charge. So you know, in between two atoms there is a region which is called internuclear region in a simple diatomic molecule, where actually electrons of the atoms, they can see the nucleus of both the atoms simultaneously. So there will be a attractive force in between those nucleus and then the electrons present in the atom. So a stabilization occurs, and that's why the bonding orbital will have the lower potential energy. So this way you can understand why the bonding orbital is having the lowest energy. Now let us learn how to calculate the bond order. So bond order is equal to, there is a formula which is called bond order is equal to half of number of electrons in the bonding orbitals minus number of electrons present in the antibonding orbital. So we have to fill up electrons here, then we have to calculate how many electrons are present in the bonding orbital and how many electrons are present in the antibonding orbital. Then if we can put those number of electrons in this formula, we will be able to calculate the bond order of a molecule. As you know, while forming the molecular orbitals, there is a attractive force between the nucleus and the electrons, and there is also a electron-electron repulsion takes place. So I will tell you here an interesting fact that will tell you the fact that there is a presence of electron-electron repulsion. You see here, this is the sigma bond formed due to overlap of the atomic orbitals along the molecular axis. So when we consider the formation of the H2 plus molecule, so you see here, this is the H2 plus molecule. Here one S or atomic orbital is vacant, and this is basically H plus, and then this is H. So it has one electron. So when the molecular orbital is formed, in that one electron is present in the bonding orbital, and experimentally it is found that the bond energy is 270 kilojoule per mole for H2 plus molecule. Now we see that one electron lowered the potential energy of the nuclei. So this is one electron present here, so it is actually basically lowering the energy up to 270 kilojoule per mole. So it is expected that when there will be two electrons, then how much energy will be lowered? It will be 270 into 2, so it should be 540 kilojoule per mole. So when this happen, actually you see, when we form H2 molecule, there we have two electrons present in the bonding orbital. So in this is for one hydrogen, this is for one hydrogen, one electrons are here, and in the bonding molecular orbitals there are two electrons. So you can say that here the stabilization should be of actually 540 kilojoule per mole. But you see here, like 2H plus, there was zero energy was 0 kilojoule per mole. Then add one electron, it lowers the energy to minus 270 kilojoule per mole, what we have seen for H2 plus, and then for H2 this should be what? This should be minus 540 kilojoule per mole. So up to this, but actually experimentally we see when we add one electron to this system, we get the energy is minus 452 kilojoule per mole. So you can see that it is not getting doubled. So experimental value for bond breaking is only 452 kilojoule per mole. So presence of two electron in the same orbital actually gives rise to a repulsion that against the stabilization. What is the meaning of that? So in this molecular orbital, you see there are two electrons present and there will be repulsion in between these two electrons. So the system will not be stabilized as we expected. So there is a slight destabilization. That's why we get the energy is lowered only up to minus 452 kilojoule per mole. Now let us just look at some of the bond order of some of the simple molecules, like in H2 plus where we have seen that only one electron is present in the bonding orbital. There if you calculate the bond order, then what will happen? Then it will be only half of number of bonding electron. What was that? That was 1 minus number of antibonding orbitals, electrons in the antibonding orbitals, that was 0. So bond order is half for H2 plus molecule, which is written here. You see for H2 we had 2 electrons in the bonding molecular orbital, right? So we had half into 2 minus 0, so it is 1. So for H2 we have bond order 1, and similarly you see here we have He2 and He2 plus. So this is for He2 helium. So helium we have electronic configuration 1s2. For one helium we have 1s2, and for another helium also we have 1s2. So we have written 1s2, 1s2. Now combine, and this will give rise to one bonding, another antibonding molecular orbital. And if we fill up the electrons, so total we have 4 electrons. 2 plus 2 is equal to 4 electrons. Now these 4 electrons will go, 2 of them will go to the bonding molecular orbital and 2 of them will go to the antibonding molecular orbital. So if we calculate the bond order here, what will happen? That will be a half into 2 minus 2. So that will be equal to how much? Will be equal to 0. So for He2 molecule we have bond order 0. But for He2 plus, what we see? We have 2 electrons in one helium and 1 electron in He plus. So there you have 1 electron, but in He you have 2 electrons. So 2 and 1. Now you fill up the electrons in the molecular orbital. You will see there are 2 electrons and here is 1 electron. Now you calculate the bond order for this He2 plus molecule, and here you see half into bond order is equal to half into number of electrons in the bonding orbital. So 2 minus number of electrons in the anti-bonding orbitals, that is 1. So what will happen here? That means bond order becomes half. So bond order becomes half. So from here you can also tell that He2 does not exist, which was a drawback of valence bond theory. In molecular orbital theory you can say that there is no bond formation as the bond order is 0. So you can say that He2 does not exist. And but we can also explain that why He2 plus exists, because there is a positive bond order. So what is that is half. So you can understand that why He2 plus exists but He2 does not exist. So from this we can say that why the noble gases are monoatomic in nature. So I will stop here, and in my next lecture we will be learning about the construction of some of the homonuclear diatomic molecules, MO. We will be learning how to draw the MO and how to fill up the electrons in there.